Hello and welcome back. If you follow the channel, we know that we are attempting to restore this HP 182 oscilloscope from 1972, part of the HP 180 series of early high-performance transistorized oscilloscopes. We spent the two first episodes repairing the mainframe after we suffered a slight electroboom incident. Then we turned our attention to the plugins, which are the original set released with the first HP 180A scope in 1966. We are starting with the HP 1821A horizontal plugin, which does not want to trigger. So far, we removed a shorted diode that did not exist in the schematics and repositioned a smashed transistor, and verified that the first page of the triggering system did work as intended, delivering the required sharp triggering pulse to the second part of the schematics that is supposed to generate the horizontal sweeps. That circuit is arranged in a large loop with a few sub-loops, and we are now convinced that there is a fault somewhere in the loop. So I see the trigger pulse, but then the trigger pulse should trigger a whole bunch of events through this loop, and it doesn't. Let's try our best to understand this clever loopy circuitry. Our main sweep generator starts with a weird bistable component, the tunnel diode CR201. It is normally biased forward, but barely, resulting in its cathode being almost at 0 volt. Upon receiving the negative trigger pulse, the tunnel diode should change state abruptly, still conducting the same amount of current, mind you, but at an increased voltage drop of half a volt, bringing its cathode to minus 0.5 volts. Moreover, it will memorize the state and stay there even after the trigger pulse is gone. Such is the magic of a tunnel diode negative resistance. This should produce our gate signal, a small negative half volt step which we don't observe. Most likely we don't see it because the loop feedback from the Schmitt trigger is wrong and our tunnel diode is not biased properly to exhibit its bistable behavior. At least that's my working assumption right now. This negative step should then be amplified by Q201, then inverted by Q202. We should now have a big negative gate step that is sent on to the blanking circuit, making our beam visible. The negative voltage will also backward bias diodes CR211 and 215. This will essentially disconnect them from the sweep generator, which they were holding previously at reset. Our sweep generator, now free of its diodes shackles, will start to sweep and move the beam across the screen. The sweep generator consists of an operational amplifier made with transistors Q207, Q208 and Q209, a current source Q206, and a capacitor. This most important last component, the integrating capacitor, is almost invisible in the schematics. It's drawn in dotted lines where it says C501 to C510. These are the various capacitor values that are switched by the big sweep rate rotating knob. Some of you might have recognized this circuit. It's just an analog integrator made the manly way without any integrated circuit. It's really just an op-amp with a cap connected between its input and its output that forms an analog integrator. A constant current source is added at the input. The analog integration of a constant current input is a perfect linear voltage ramp at the output, which is our desired horizontal sweep. This is then applied to the horizontal deflection plates and our spot will sweep across the screen very linearly. But we need a way to stop the sweep once it arrives at the right edge of the screen. That's the role of Schmitt trigger Q204, Q205. It monitors the sweep voltage. When it gets above a preset value, which is adjusted to match the right edge of the screen, the Schmitt trigger output flips. The Schmitt output is then fed back to the tunnel diode, which should somehow reset it to its starting state while turning the gate signal off. This turns blanking on and reconnects our shackling diodes CR211 and CR215, resetting the sweep and causing the beam to fly back to the start position. Unfortunately, the way the sweep is monitored by the Schmitt trigger is complicated. First, the sweep is scaled down by a resistor network. Then there are two different paths. The first one is through diode CR216, which forwards the scaled down sweep to the Schmitt trigger input. When the sweep reaches the right edge of the screen, the Schmitt trigger should flip. But there is another path, used for the hold-off feature. Along this path, the scale sweep is first buffered by the hold-off emitter follower Q210, Q211. It then goes through a maze of diodes, resistors, and caps. The output of that maze is applied to the Schmitt trigger input via diode CR217. It's not entirely obvious how that works, but the result should be a temporary signal that holds the Schmitt trigger in the reset position during the traceback, so the gate cannot re-trigger during that time, hence the hold-off name. You can also see that this circuit is used for single sweep operation. Well, that's it. That's our universe for the next critical part of our debug. There is a fault in this giant loop somewhere, we just have to find it. So something is wrong in this big loop, which means at some point we need to open it up. Actually, KindHP gives you a way to test it without breaking the loop. Bypass this by forcing this either to ground or to minus 12.6 volts. If you look at the DC levels, there is one that's marked without parentheses, that's the one where this point is grounded. And there's one with parentheses, that's when this is held at minus 12.6 volts through a 1K resistor. I won't bore you, I did the experiment, and all the voltages match up to here. So my guess is this is working, and now we get into the sweep circuitry. And my hunch is that the sweep circuitry is working too, because in some cases when I was tweaking the button I got one sweep. So I already have an inkling of what's happening. I think this works because I saw the dot moving across from time to time. It goes up and then the dot is stuck somewhere, I think towards the right of the screen, and somehow this cannot detect the end of the sweep and never resets. That would be my working assumption. But to know that that's easy, I just go over here, which is the output to the horizontal deflection, and I'll be able to see where the dot is. It's either stuck at 0 volt or at plus 38 volts. So I'm now going to test at TP205. That's the output of the whole shebang. And finally we move up to the upper card, actually not very far from where we had the previous repair done. And that's the test point. And let's see where our dot is. Oh, that's excellent. Did you see it sweep? So it does sweep. And it gets stuck to the right, exactly as expected. Can I make it faster? I sure can. Oh, so it wants to sweep. All right. I wonder if I could see it actually. So what I have to do is turn it on for a while so the tube... Ah! Did you see it? I saw it. There it goes. More intensity. Do it again, Sam. There. Very excellent. It gets stuck to the right. And it's not resetting. Oh, that is excellent news. So it's not detecting the levels, and it's in this loop here. Or this also could screw it up. So there is a hold off emitter follower that prevents it from being re-triggered too soon. Let's see if the levels are correct on the feedback loop here. Alright, we are finally going somewhere. Looks like the Schmitt trigger is not reading the end of the sweep. So I am going to make sure it gets the right signal along the red and the purple path. First step, making sure the red is a scaled down version of the green sweep. So I'm going to monitor these two signals. Let me recolor them so it matches the color of the traces on my scope. Red will be the sweep, blue will be the scaled sweep. At this point, since it's just resistor scaling, I don't expect any fault at all. I just want to confirm that I understand the circuit correctly. And we're getting dangerously close to the section that somebody was trying to repair. I'm expecting the red line, the blue line to move in unison, but just shifted a bit. And they wait. It started good and something not good happened. So they move together. And that stops at minus 12 volts. That is not correct. I have it here actually, by pure luck. Yeah, it stops at minus 12 volts. Yeah, it should stop at minus 5.5. I bet you that's our problem. That never goes to minus 5.5, so that never goes here, and that never resets this trigger. Something is holding it down. Something is holding that line at minus 12 or something. I'll just desolder this and see if this returns it to normal. If that is, then the fault is in this line and it's being clamped by that diode. Okay, let me desolder this and see if we get our level back to normal. Aha! Our symbol resistor scaling of the sweep does not work. Or more exactly, it works for a while, then it gets stuck. Feels like a diode is turning on at some point, and my bet is on CR216. Let's desolder the cathode side of CR216. That should isolate the blue line from whatever I suspect is holding it at minus 12 volts on the other side of the diode. I got it. Alright. So, no more CR215. And I'm expecting the two lines to follow each other. Yeah, now that works. So at minus 5.5 it should have triggered the reset. So something is holding that at minus something. So see what it is here. I expect minus 11 volts or something. There you go, now the blue line is behaving. I bet you my weekly allocation of bananas that this line here is stuck at minus 12 volts or something. I already know what's happening because I tried it, but I didn't press the record button. Reenact the experiment. I measure minus 13 volts. Alright, it's confirmed. This line is indeed stuck at minus 13 volts. And there are only two wires connected to that node. I can smell blood. We are closing in on the kill. So is it coming from here or is it from there? More likely it would be the hold-off circuit that's not working. So it would be coming from here actually before being added on the line by diode CR217. One way to tell is to disconnect the anode of CR217, which would disconnect the hold-off circuit entirely. Hold-off is not really required and does not spring into action until the end of the sweep anyhow, so maybe I'll get one sweep. So something brings this side minus 13 volts. As soon as it reaches minus 13.6, this diode turns on, and then it gets pulled down by this and never raises, right? Either this side is pulling it down or that side is pulling it down. Let's make sure the hold-off emitter follower is not causing it. I think I could make it work one sweep and see if we go back if we remove CR217. So wouldn't you know it, CR217 is where we were before with the short, and CR217 has already been changed. It's here. I think we are revisiting a fault that was there that somebody tried to repair and he got almost close to it, but somehow it didn't work, and then this one got tossed, and then 40 years later I got it. All right, let's look back at my red line and if we see if it's still clamped. Minus 9.2 volts, that ain't any better. I'm not seeing it sweep anymore. Let me reconnect the diode for a second. Huh, my sweep is back. That complicates my life because the sweep is not working. So there might be a double fault. There might be a fault here and there might be a fault here. Oh, wait a short second here. this should change from minus 12.3, which would explain why I have minus 13 here. But this should go up to minus 3.6 at the end of the sweep. That was inconclusive. It doesn't want to signal sweep anymore. Looking back at the footage, I realized that I forgot to reconnect CR216, so maybe that is part of the issue. But as you'll soon see, the fault is just too devilish. So for now, let's reconnect CR217 so we get back to our signal sweep situation and investigate the hold-off circuit another way. The transistors Q210 and 211 form an emitter follower, so I should find an exact copy of the scaled blue sweep signal if I monitor the emitter of Q210. Hold-off emitter follower. So let's test this, because this is just an emitter follower. So I should see my blue signal repeated here. All right. And we are right back in the circuit where this was monkeyed with. So now the red and the blue should follow each other. Let's do it. All right, well, we have a fault. The red is not following the blue at all. It's at minus 88 volts. What? So I'm here, I should start at minus 25 volts and go up to minus 2.6 volt as it ramps up. And I am stuck at this super low voltage, which is very, very low. It probably blew everything afterwards. Okay, Q211 and Q10 get out of the box, I guess. So it's in the section that was reworked. My hold-off emitter follower Q10, Q11. And before we get too excited here, we need to figure out what Q210 is. 1854-0083. It's made by HP, and of course there is no equivalent. But I found it in my fish, which by the way, they have been scanned and uploaded. There it is, 083. So 30 volts, 360 milliwatts, 250 megahertz at 50 milliamp, 50 to 150 gain at 50 milliamps. So it's a transistor made to work in the few tens of milliamps. 800 milliamp max. VSAT not that great, 0.8 at 100 milliamps, so it's meant to be driven relatively hard. There's no equivalent to this, but I would bet you a 2N2222 would do perfect here. It's about the same frequency, and it's made to drive quite a bit of current too. Alright, the two transistors have been extracted. I spared you the surgery. Turns out Q10 is zapped. I have an open on one of the junctions. This one looks like it's still a transistor on the ohm meter test. These are PN222A. We can see what an original looks like and compare it on the curve tracer with our PN222A, the modern version of the 2N222A. On the left, the original HP transistor. Looks good to me. On the right, PN2222 looks, it just has more gain, which is nothing wrong in an emitter follower. It will follow better. So that's a good replacement. One of the originals still had transistor mojo. And then Q10 gets an upgrade. Or modern replacement. Also the 2N2222 is a very old transistor. It's from the 60s. Okay, let's see what we repaired. I don't think we repaired everything. Let's see if we have recovered an emitter follower stage. It follows. Oh, something has changed. So we have repaired something. Let's try it. Woo-hoo! Did I see some smoke? I saw some smoke. Yep, not sure was magic smoke. What's wrong with the scope? We got electro boom, then a diode popped, and now this. Are we cursed? So what I saw here is that the trace came and went back. At the same time, I was going to show you that some smoke came out of the circuit. Yeah, those transistors are super hot. Yeah, transistors are hot. So something is blowing the transistors. So this is more complicated than I thought. I bet you it's Q10 that blew again. And it worked for a short while. Well, that's really weird. Unexpected. Okay, well this is that our third smoke event? Of the whole thing? Gee wee. So took the transistors out again, and it's as before, Q210, the one that died before, it blew up again in a similar way. It's an open now, so it's an overcurrent. So something here causes a terrible pain to this transistor. That resistance burned out. This diode, not a diode anymore, I just checked it. Okay, never a dull moment. Dang it, we were progressing for a while, now we're regressing again. Okay, I've been poking around a bit, trying to figure out what could cause our transistor here to be zapped. And when I started to measure around here, it was bizarre. It turns out I have a short from that point 8 to minus 12.6 volts. If I go here, and I go on power supply 12.6 volts. Direct short, 0.0 ohms. So looking to resurrect the sweep at the emitter follower, we replaced Q210, and that seemed to have worked for a short second, after which it promptly blew up again. Looking around at what could cause Q210 to blow, I discovered a dead short to the minus 12.6 supply at point 8. To make sure, I disconnected CR217 again, and the short is still there. It's real. But where the hell could this short come from? There is nothing connected to minus 12.6 in this circuit whatsoever. We are definitely cursed. So that thing was at minus 12.6. There was no resistor to protect the poor transistor, and it blew. And I removed that CR217, so it's just isolated here. There is no 12.6 volts around. Looking for possible points of entry and having eliminated the nearby onboard components, I discovered that there is a pin hooked up to a wire under the board at port 928 that disappears in the bowels of the plug-in. I wonder if the short could come from there. So I removed that resistor to make sure it wasn't coming from there. It's a pin over there. So I need to take this whole thing apart and look at what's going on back there. It shouldn't be connected to minus 12.6 volts at all. Yep, I plugged the wire from the connector on the other side of the board. And it's shorted to minus 12.6. Where does it go? Normally that wire should go to a switch of some sort that switches in capacitors C514 to C520, I suppose to change the duration of the hold-off depending on the sweep speed.
1 hour later.
Alright, after an hour of searching, I think I might just have found it. And I had to take it fully apart. So that's the wire that should not be attached to minus 12.6 volt and is. Then it goes at the back, it goes, I lost it for a while, but then I found it. It goes back through the board right here. And it goes all the way to that rotary switch here. It's on the common back there. And if you look at the rotary switches, it goes exactly where it should be. It goes here. It says to junction R254, R255. That's where I found my short. and it comes here, and it switches all these caps here to ground. So depending on the speed, the hold off time is changed. And there is no minus 12.6 volts in there at all. Then finally I looked at this guy over here, and this is minus 12.6 volts. So my theory is that this is touching something it shouldn't. Okay, it's connected to minus 12.6 volts, but also connected to my wafers with all the caps. And my theory, untested, but we'll know in a second, is that this has been pushed in, and it should be like this. And now let's try my cap again, and minus 12.6. And the short has disappeared. Minus 12.6 is here. It's not there anymore. It's not on my wire anymore. So that was probably the root cause of this whole mess. Oh my, this guy got pushed in. Okay, well, at least it's none of my doing. I was worried for a minute. Alright, it's been isolated. Now I just need to put it back together, which, man, was so difficult. We should be back. Alright, transistor repair the second. And I'm still disconnected here and here. I'm disconnected here, so that part is not going through, and I'm disconnected here. So the circuit is totally isolated at this point. See if it still blows up or not. So we are watching for the blue following the red this time. Not doing a thing. We don't have any sweep. But maybe that's normal. Maybe there is no sweep because I have disconnected. I think this was sort of necessary for the sweep to operate. Let me reconnect it quickly. Alright, after the battle we ended up in a little bit of a disheveled state. We should have gotten rid of the short on wire 928, so the minus 12.6 volt fault should have been removed. We replaced transistor Q210 for the second time, so I am looking to see if I have recovered the sweep at the emitter. But I still had CR217 disconnected, so let's reconnect that, which should bring that part of the loop back into service and hopefully start a single sweep. Now, yeah, okay, red follows, I have to put them on the same scale, red follows blue. We have an emitter follower. All right. Oh, I haven't reconnected CR216. Yeah, our emitter follower sweep is back, and we have not released any extra magic smoke. Let's now reconnect CR216, which should restore the main loop path to the Schmidt trigger, and see if we finally can get it to detect the end of sweep. Okay, I'll temporarily reconnect CR216. And the reason I'm doing it temporarily is that if the line is still pulled down, I will have to redisconnect it to figure out what's pulling it down. There you go. Got it. Okay, so we have repaired this and reconnected it. Let's see if I reconnect that, I get to my all the way to 5 volts, and The thing works. So now it's the red line. Let's see if it clamps. Oh, it goes up and down. We have, yeah, we do have, oh, we repaired it. Yeah. Okay, that's what was wrong with it. Can we trigger? You bet. Can we vary the trigger position? We can. It's a little scratchy. It's a little scratchy, but I have my probes on it, so that's probably causing a little bit of trouble. Now the next thing I have to check is the delayed time base. And the delayed time base seems to work. So I can change how much the second trigger, how fast it goes. Then I can only show either the normal or the delayed and the mixed. Everything works a little jittery, but I think it's because I have my probes on it. Alright, never a dull moment. I was calibrating everything now that it's done, and the regular sweep calibrated perfectly, no problem. Yay, calibration time! It's finally time to tweak every one of these adjustments. There is one for each sweep range, both main and delayed, which is why there are so many. It's tedious but not difficult, and very well explained in the manual, except it didn't quite go as planned. However, on the delayed sweep, I couldn't calibrate it. Then I checked on the schematics, and sure enough, I checked that the voltage here was changing with every resistor, so that should have changed my sweep time. But when I went over here, that was not changing, so this transistor was not being a current source. This little guy over there, and in circuit it measures completely dead. I have no junctions whatsoever. Remember our sweep generator with an integrator and a current source? You can adjust the sweep time in two ways, by tweaking the capacitor or by tweaking the current source, which is what many of these red and gray pots should do. Except they didn't. Turns out my current source wasn't a current source anymore. And of course, the other proprietary transistor, another one that's in my fiche, and it's a current source, so you don't need very much. So I could replace it with a 2N3906, but I have an HP transistor from that's exactly the same, except it's a little faster. This one, that's the 09, and I'm replacing it with an 034. That's a few lines down there. It's all the same parameters. It's almost identical. Alright, so one more dead transistor, and I think there's one more after that, because I cannot have it work on single sweep. So one more fault remaining, even after this one. Okay, see if we can calibrate now. Alright, and that did work. Our calibration capability returned. So it's pretty simple. You give it a train of pulses so I'm calibrating 50 microseconds. They want a scope calibrator, but I use my trusty Keysight. Difficult to operate, but very precise, this later instrument.
A few moments later.
So we are now calibrated, and we are left with just one fault, which is that it doesn't do single sweep. It should stop here. So it does the normal, so it can stop the sweep for sure. And then if I do auto, it will sweep in auto. And if I do single, interesting, it stops if I have nothing, but it will still trigger, and it should have only triggered once. Okay, I am thinking it might have to do with the freaking diode that burned at the beginning, because it's in the hold-off circuit, which is responsible for the single sweep. And the more I look at this, I discover that mine is a more recent revision of the board. There's stuff that's different. And the fact that it burned might have been related to the other short that we had that also burned the transistor. So I am wondering if this is necessary in this version of the circuit. After lots of searching, I managed to make my single sweep work. You can see it seems to be a contacting problem. In order to do that, I had to disable all the other modes and lift this diode over here. So what's happening according to the schematics, there's a little switch here that goes normal, auto and single. And in single it disconnects the output of the hold-off emitter follower from the Schmidt trigger circuit over here. I found that the switch was not doing that. This kept being connected to that, so I just disconnected it and now it works, but of course I've lost normal and auto. I have to spend another hour and dismount everything. There's another short in the wiring. That would be our third short. Yeah. So I have to get all the way into here. So I have to figure out what's wrong in the contact buried in here, and the wiring is super tight, super difficult to reverse engineer it. But I did it once to find my short, so I should find short number 2. Alright, I had to remove a few components that were in the middle, but after some advanced surgery I was able to go and see the switch at the bottom. Is that guy over here, and it has 4 wires to it. There's a wire that goes straight to where our mystery diode was. It's a mod that has been added on purpose. On my revision it's not wired at all as they say. None of that is used, so instead you have a contactor that uses this diode, and in single mode it grounds it, so that disables this point, that puts it at ground. In violet and auto it's connected to minus 100, and this diode will just not be there. It will be not conducted, and it will have the regular circuit and it will go through the permanent connection. Interestingly enough, the reason it blew, now I can tell, is because this node had a short to minus 12.6 volt, and when it was in auto mode you have minus 100 on one side and minus 12.6. I shouldn't have done anything to the diode because it should have been reverse biased. Oh no, I know what happened. Oh, it's a two-step fault. I switched it to single mode. It was shorted here to minus 12.6. No, 0 volts on one side, minus 12.6 on the other side. Smokes the diode.
Flashback.
I was trying to figure out if I could get it to reset in single sweep mode. I heard a distinct small pop towards the back of the instrument.
End of flashback.
Then I switch it back to auto, and now that diode is a short, and my 12.6 short here has a second short here that shorts to minus 100 volts and disables my power supply. Oh man, talk about the Swiss cheese thing. So the short blew this transistor, and then it blew that diode, and then when I placed it back over here, it shorted my power supply. Gee wee. So I think all I have to do is put a diode that can take 100 volts, a little bit more, over here in the right polarity, and I reconnect everything and that should work. I'm not sure if you followed the contrived explanation, but I can now reconstruct the sequence of events that caused so much damage in this plugin. First of all, the single sweep is not implemented as drawn on the schematics. I have a later revision, and in my unit there is no switch that disconnects the hold-off from the Schmidt trigger when in single sweep. Instead, the hold-off circuitry is permanently connected to the Schmidt trigger. However, a mystery diode has been added. In single sweep, the other side of the diode is tied to ground, it becomes forward biased, and it grounds point 8, disabling the hold-off circuit. In all other modes, the diode is reverse biased and becomes essentially invisible to the hold-off circuit. Problem number 1, they chose minus 100 volts for the reverse bias. Why not a kilovolt while they were at it? Second problem is, a contact strip had been smashed in, causing point 8, the other side of the diode, to be shorted to minus 12.6 volts. Now in normal mode, having minus 100 volts on one side and minus 12.6 on the other would not do any harm. The diode would just be reverse biased and non-conductive. However, when I moved the lever to single sweep position, it switched the other side of the diode to ground. Suddenly our diode was forward biased between ground and the minus 12.6 volt supply. Predictably, it blew. To make matters worse, it didn't blow as an open, it blew into an almost short. So, when I returned the lever to the normal position, now I had minus 100 volts, shorted through a blown diode, shorted to a contact strip, shorted to minus 12.6, which took down the minus 100 volts power supply. And that explains everything. Why the mystery diode was there, why it blew, why the supply went down, why transistor Q210 emitted magic smoke. The final repair is easy, just put a high voltage diode back to where the mystery diode used to be. That should restore the single sweep operation. But I still don't approve of the design, mind you. One should not directly connect minus 100 volts without any protection resistor for the simple pleasure of reverse biasing a diode. That's just asking for a meltdown. Mr. Revision Engineer was not as gifted as Mr. Original Engineer, apparently. So let's remove our mystery diode. That's not so mysterious anymore. There we go. And I found a suitably high voltage vintage diode. That should do the trick. Alright, put it in the correct direction. And I guess it also explained all the rework that had happened here. They were looking at the right thing, just slightly off. On the other side, I have insulated my problem pin that resulted in the short when I pushed in, so we should be good there too. Will the 20th time be the charm? Okay, better works. Yeah, it works. So demo time. And demonstrate the power. Oh, I haven't retested this because I unmounted it. Yeah, it works. So that's the power of the dual scan, or the delayed time base. I go here. There you go. I'll look at it around here. And then I can look at the normal one and the expansion. And I can either unfurl it or trigger on it. I do jumps by a whole period and display the expanded portion. You know, I was reviewing the footage and I realized that I never checked again on the transistor that was smushed over there, and that's the one that drives the neon reset light that doesn't work. So maybe it's not the neon, it's the transistor, and then I just looked at it and one wire is broken, probably from the smushing. Q203, and it's an 1854-022. It's not critical, but it needs to have the voltage. I happen to have it. It's an 80 volt transistor, as I expected. Any other 80 volt NPN in a can that looks like that would work just fine. Thank you very much. But since we have the exact replacement, that's what we're going to use. I forgot to press the record button again, but I changed the transistor. There it is. Will that bring us perfection? So, hey, it came back. We are 100% back. Ho-ho! It's 100% repaired. Very excellent. Beautiful scope. I love this large screen, but man, was it difficult. I put it in the category extreme. Everything that was bad in the high voltage power supply. All this that was bad in the gate control. And then finally, in the timebase, not that bad. 3 transistors and a diode, but it was so hard to find because it was caused by a short that did all kind of horrible things to it. I tell you, the result is well worth it. But I just like to unfurl my little guy. For now, I think it's done. See you in the next episode.